Hi everyone! In today's lesson, we're going to be going over Atwood machines and pulleys and how to set up and problem solve questions that include Atwood machines. So what is an Atwood machine? An Atwood machine is kind of like a lab apparatus, which I've drawn to the right, in which two objects of mass 1 and mass 2 are connected by one massless string over an ideal pulley. So what makes an Atwood machine or pulley ideal? So the first thing is that the pulley is frictionless. That means the rope that slides over it does not experience any friction. And the mass of the pulley is zero. It's massless, which in real life this is not possible, but that is why we call this an ideal pulley. So an ideal pulley creates a property in the string that connects the two masses together. Because the pulley itself is frictionless and its mass is zero, and also the string is massless, the tension throughout is equal. So tension throughout the pulley is equal. This means that mass 1 experiences the same tension as mass 2. Okay, so now that we know what an Atwood machine is and the special properties that an ideal pulley creates, let's talk about some ways that we set up F-net equations for problem solving. So there's two ways that we can set up a F-net equation. One is if we take the entire pulley as one system, or another way is to set up a F-net for each mass. First, let's start off with setting up an F-net for each mass. When we draw free body diagrams, we know that mass 1 experiences a tension and also a weight m1 times g. Mass 2 also experiences that same tension because of the properties of an ideal pulley and also a weight of m2g. What we need to remember here is that mass 1 and mass 2 are in the same system. And because they are in the same system, mass 1 and mass 2 have the same acceleration. That way I can say acceleration for mass 1 is equal to acceleration for mass 2, and in turn I will just call this an acceleration of A. So now let's set up an F-net equation for mass 1 and mass 2. Because we don't know which mass is bigger, we're going to have to decide which way our pulley is accelerating. I'm going to assume that the pulley is rotating this way, such that m1 is accelerating down and m2 is accelerating upwards. If our assumption is wrong, the math will end up giving us correct because the F-nets will still be chosen and the negatives that we chose incorrectly will cancel out. So as long as you assume the direction, you have to keep that assumption consistent for both mass 1 and mass 2. So F-net 1 is going to be m1g, the weight of our block, minus the tension because it's opposite to the acceleration, and that's equal to m1a. For F-net 2, we know that our m2 is moving this way because our m1 is moving this way. That means we will have t minus m2g equals to m2a. And once again, if we're assuming that our pulley is rotating like this means our m1 is falling or accelerating down, and our m2 is accelerating up as m1 accelerates down. So we don't know what t is usually, and let's say that we want to solve for acceleration. We can isolate for t using any of these equations. I'm going to use F-net 2. F-net 2 tells me that t is equal to m2a plus m2g. Now I'm going to plug this t back into my fnet1, and I will have m1g minus m2a minus m2g equals m1a. The purpose of this is to solve for my acceleration. So I'm going to put in all the variables with a onto one side so that my equation looks like m1g minus m2g equals m2a plus m1a. Factoring out my acceleration and my g, I will have g times m1 minus m2 equals to a times m2 plus m1. Now, in order to solve for acceleration, I just divide both sides by m2 plus m1, such that my acceleration is equal to g times m1 minus m2 divided by m2 plus m1. Okay, so let's put that idea into use into our first problem. Two objects are connected by a cord of negligible mass that passes over a massless, frictionless pulley. When the objects are released, the object with mass 0.7 kilograms accelerates downward at 3 meters per second squared. What is the mass of the other object? So the first thing that we need to do is draw our diagram of what's going on. So we know that there is a pulley with two masses. One of them is 0.7 kilograms and the other one is unknown, which I'm just going to call M. We also know that the pulley is rotating or accelerating this way, such that the 0.7 kilogram mass accelerates downwards at 0.3 meters per second squared. Since our pulley is ideal and the tension in the string is equal, we also know that the acceleration of the system is equal. And so the unknown mass m has to accelerate upwards at 3 meters, 3 meters per second squared, because they are part of one system. The pulley is only changing the direction of that acceleration. Okay, so we know that the forces acting on both the 0.7 and m are T, and they have the same tension because the string is massless, and also 0.7 g for the weight or the gravitational force on the first mass, and just mg, which is the gravitational force on the other mass. So A and B kind of go together. If we want to find the mass, we kind of find the tension at the same time. So let's first set up our Fnet equations. We know Fnet1, which is for our 0.7 kilogram mass, is mg, which is 0.7, times g, minus the tension in the string, equals to ma, and that's 0.7 times the acceleration of 3 meters per second squared. Next, we have Fnet2, and that is the equation for the unknown mass. We know that since this one's accelerating upwards, we should have tension minus its weight equal to ma, and since a is 3 meters per second squared, this would just be 3m. From Fnet1, we can solve for the tension by moving over the tension and having 0.7 g minus 0.7 times 3 equal to t. And let's plug this into our calculator. 0.7 times 9.8 minus 0.7 times 3 gives us a tension of 4.76 newtons. And as you notice, we kind of solve for B first instead of A. So using the information that we just found, tension is 4.76, we can plug this back into our F net 2 equation. So our new F net 2 will look like 4.76 minus mg equals to 3m. Since we're trying to solve for the unknown mass m, we're going to move all the parts of the equation that have m to one side, so that our new equation looks like 4.76 equals to mg plus 3m. Now we're going to factor out the m from that one side, such that our new equation is 4.76 equals to mg plus 3. And m is going to be equal to 4.76 divided by g plus 3. And let's plug this into our calculator. 4.76 divided by 9.8 plus 3 gives us a mass of 0.37 kilograms. Okay, in this next problem, we're going to look at our problem-solving method in a new way, where we take the entire system as a whole and disregard internal forces. So, a 10-kilogram box rests on a horizontal surface with a coefficient of kinetic friction of 0.2. The 10-kilogram box is attached to a 5-kilogram box through an ideal pulley. What is the acceleration of the system? So, what a pulley does, again, is that it just changes the direction of the force. There is a force mg acting on this 5-kilogram box, and there is a kinetic friction acting to the left of the 10-kilogram box. The internal forces are the tension in the string. But what the pulley does is that it changes the direction of the tension acting on the 5-kilogram box, such that that same tension acts horizontally in the x direction on the 10-kilogram box. So what we do here is that we disregard this little piece. And all we know is that, let's say our system is the total mass 15 kilograms. So we have F net, right? And the force acting this way would be mg, and the opposing force would be F sub k. And because we're taking this entire system as a whole, we're adding the two masses together, such that our F net gives us 15a. And we can do this because our system has the same acceleration for both blocks. And just so we're not confused, this m right here is the 5 kilogram. So that's all we have to do to find the acceleration, because the acceleration is the same for both boxes. So we know that our 10-kilogram box has a weight mg. And because it's on a surface, it has an equal normal force up because it's not flying upwards. So N has to be equal to 10 times 9.8, which is 98 newtons. So therefore, our Fk would just be mu times 98. So our F net equation is going to be 5g minus mu times 98 equals to 15a. And solving for a, we would have 5g minus mu 98 divided by 15. So let's put this in our calculator. We have 5 times 9.8 minus 0.2 times 98 divided by 15. And this gives us an acceleration of 3.12 or 3.136. Oh, sorry, 3.136 meters per second squared. Okay, part B is asking what is the tension in the rope. So now that we want to find the tension, we just need to look at the internal force of just one of the blocks. So the easiest one that doesn't have friction is the 5 kilogram block. And because it's accelerating downwards, I would say the F net is the 5 kilogram block times 9.8, which is mg, minus the tension is equal to ma. And we already solved for a, so this would be 5 times 3.136 meters per second squared. So all I would do is rearrange the equation to isolate t, and I would have 5.5 times 9.8 minus 5 times 3.136 equals t. So let's put this in our calculator. 5 times 9.8 minus 5.5 times 3.136. And this gives us a tension of 33.32 newtons. Thank you so much for watching, and I hope this video helped. If you want practice, there is a document with practice problems linked in my Forces 2D video that includes pulleys on inclines as well. In the next lessons, we will be going over pulleys and other forces that act on inclines in one problem together. Thank you.